Okay, so maybe let's start with parametric mode. So this is notebook 04 of the tutorial. So in parametric mode, the pipeline is run multiple times with different parameters that are specified in the YAML configuration file. And we use the library Xarray to save the output data for each of those parameters or parameter combinations in the end into a dataset. By the end of this lesson, you will know how to prepare the configuration file for parametric mode, how to run parametric mode. There's actually 3 modes of parametric mode, and we're going to see in a minute, and how to inspect and save the parametric results. And before I forget, we also updated the README file in Pyxel data repository. So there is a bit more information on how to clone Pyxel data repository if you're not using Binder and if you want to use your local installation of Pyxel. For that, you have to install kit LFS. There's instructions here, and then you can download Pyxel data manually with a zip file or via Pyxel. Okay, let's go back. So there's, as I said earlier, there's 3 different modes of parametric pipeline, and the default mode is called product mode. So we have to specify in the parametric YAML file how to which parameters do we want to iterate over. So in this case, if we have a model that has argument called argument1, and this model is in photon generation, for example, we can specify that we want to iterate over values 1 to 3, and we also want to have a change the parameters of another model that's called model 2, and it has argument 2, and we want to iterate over ABC. So in this case, the pipeline will run 9 times, and it will change parameters for each of the combinations of those 2 lists. So in this case, the first pipeline run will have argument 1 equals to 1, argument 2 equals to A, and then it will change the second argument, so it will be 1B and then 1C, and so on. So we see that this is like a product of 2 vectors. Okay, so what can we actually put into this for values? We can put lists. We can put lists of strings, lists of numbers. We can also input a NumPy function like this. So in this case, we will try to put in the NumPy linspace. And we also allow to input lists of lists, and we will see how this works later on. Another mode is sequential mode. So in this case, the pipeline will not run 9 times, but 6 times. So in the first, we will change the argument 1 to 1, 2, 3. And while we are changing argument 1, the argument 2 will stay default. And by default, I mean the one that we specified down here in the pipeline. And next, argument 1 will be set to default, and we will only change argument 2. So we will go with argument 2 from A to C. And the third parametric mode of parametric mode is custom mode. This is when we want to upload parameters from a file. In this case, if we have a file called parameters.txt, and there's rows in the file like so 1A, 2B, 3C, then we can specify in the YAML file that we will load parameters from file, parameters.txt. We note with this underscore that we will read those parameters from the file. And what it does, it's gonna read this file row by row and change the arguments like so. So first run of the pipeline, the parameters are going to be 1 and A. so the argument 1 and 2, and then 2b, and then the last 3c. So the pipeline is gonna run 3 times in total. Okay, so let's see how it works. We will go through all the 3 different modes. And for the first, we will see the product mode, since it's the default mode. We will change, so we will use stripe pattern illumination model. What this will do, instead of loading an image, we're gonna construct a stripe pattern, which is basically a square signal going from 1 to 0, 1 to 0, and with a certain period in pixels. We will also change the angle of this of the pattern. It will go from 0 to 20 degrees. The period we will change from 4 pixels to 20 pixels. And we will also change the arguments of the CDM model. And I'm going to spend a bit of time on the CDM model here. So CDM model is a charge distortion model that is used to simulate effects of charge transfer inefficiency. And we already heard something about charge transfer inefficiency so far in the workshop. But anyways, so radiation can cause defects in the detector which trap the charge, and the probability that this charge gets released later in time decays exponentially with certain characteristic time, which is trap release time. And we can have different traps or different species of traps in the detector that have different trap release times or different characteristics times. They can have different densities, so there can be more traps of certain species than others. And what this causes is, when the charge gets released at later time, it causes smearing and final image. So we have this, if we only observe one row of the detector or one column of the detector, we could see this exponential decay behind a bright dot or behind a star. And we will see later in the images how does it work. And it can also cause the decay of contrast in the images. Okay, so we are going to actually change the trap densities. So here we will say that we have 2 trap species with trap release times 3 to the minus 3. 3 times 10 to the minus 3. And we're going to change from little densities to higher densities. And this is going to be our parameter. Okay, and so what product mode will do, it's going to compute images for all the combinations of these parameters. And we start by importing the inputs-outputs module. We're also going to need a parametric mode function. So this is similar as yesterday. We imported single mode, but now we have parametric mode. We're going to use HoloViews now in the notebook, and we're also going to set the bokeh extension. We're also going to import opts. This is to set just the plotting options. And we will load parametric product YAML configuration file. And if we run the result, if we run parametric mode, we get this result. This result is actually a named tuple that contains multiple results. So it contains a data set. So the first one. So in this data set, we save the arrays pixel, signal, and image. We save it for different periods, for all the periods that we defined here in the YAML file. We save it for different angles and for different densities, but because because these densities are not just a one-dimensional array, but it's actually two-dimensional list, we can't really use those. This can't be a coordinate, so we just provide an ID. So it goes here from 0 to 6, because we have seven elements in this list. Okay, and maybe I should talk a bit more about X-array. So also X-array is a library that can handle labeled multidimensional data. So here we see that we save this data that has multiple dimensions. So it has each array has the dimension x and y, but also period, angle, and the ID of the trap densities. The dimensions are specified here, and also we have coordinates. So for because we have detector of size 100 by 100, x and y are lists that go from 0 to 99, and but here dimension is just an integer that is 100. We can also assign some attributes to the X-array dataset, and this is just some metadata that we can put in for information. We're gonna also see this later. Okay, so we can also explore parameters. In this data set, we save all the parameters that we used. So in this case, we actually see the value of the trap density as a function, or with ID as a coordinate. So we can actually know, even if we don't know here, we only have ID that goes from 0 to 6, but because we can't use this as a coordinate, we save this later into parameters to know what kind of parameters did we input. And this is good because sometimes models use multi-dimensional, or models use lists as inputs, and it's nice to have this capability to also input multi-dimensional parameters. Okay, and the last one is logs. So in logs we save, so here we save parameters for each of the pipeline runs. So here we saw that pipeline was run 105 times. So this was so 5 times 7 times 3. And for each of the pipeline runs, we have the ID that goes from 0 to 104. And for each ID, we can also see the parameters. So as we can see, some of the parameters repeat because we are iterating through all the combinations of the 3 parameters. Okay, and so we can plot some images here. We're going to plot the image array from the result dataset. We're going to convert this into a HoloViews dataset, and we're going to plot images from this dataset. So as a function of x and y, and this slider will be constructed automatically from coordinates that are not used here. So we're going to change here the period, the angle, and the trap density ID. And we also specify some options like aspect ratio, color map, and that we like to have a hover tool so we see the values. Okay, if I change this, I can move around, see for multiple parameters how does it change live in the image. So we also chose here that we would like to plot this dynamically. So every time it's plotted from scratch from the data set. So it's not loaded into the memory right away. And if I set this to false, it's going to be loaded in memory. And then it's a bit slower at first, but quicker when we actually load the data. So if I now make this trap densities a bit larger. We can see that the contrast degrades due to CTI. So here we have values 4,000 and 85,000, and the trap densities are high. So at this end, we have 14,000 and 70,000. We can also choose only one column in this array. So I'm gonna select by index. I'm gonna set X to 50. So we're gonna observe a column here in the middle. And instead of image, I'm gonna plot the curve. And now it's basically the same. So we have again period, and we can see, let's make it a bit bigger. And if I slide this over to larger trap densities, we can see this exponential decay here that causes the contrast to degrade. And we also see visually how contrast degrades here. Okay, so one good thing about HoloViews is that we can merge these objects just by summing them. So here we can actually see, okay, I'm gonna put this. And we can change things in parallel, just like this. And one thing that we can learn, for example, from such a parametric mode is, for example, the contrast transfer function. So how does it change with varying the period? So the spatial frequency in the detector. This is one example of how we would use this data. Okay, so next mode would be custom mode. I'm gonna open the densities here. So this is the file that I'm going to use. I'm gonna switch to the other parametric config file. So here we specify that node is custom now. We're gonna specify that we're going to load parameters from file data / densities.txt. So this one, we're going to change the beta parameter. This is the cloud expansion coefficient in CDM model. This is the first column. We're gonna just we're just leaving it at 0.3, and we're also going to change the trap densities as before, but now we're gonna have 4 traps, so 4 different traps, and we're gonna do similar as before. So low trap densities to high trap densities. And if I go back to the example. So here we again load the parametric custom.yaml. We construct all the 3 main objects in the Pyxel architecture, and we run the parametric mode, passing all 3 objects into the parametric mode function. Okay, so as before, we get the result, which is a named tuple again. If we take a look at the data set, we can see that we again saved pixel, signal, and image. And now we just have the ID of the pipeline run. So this time the pipeline ran 20 times because there's 20 rows in this densities.txt. And we have data for each of those pipeline runs, and we just know the ID here, what was the pipeline number. And if we want to know the actual parameters that were used in a certain pipeline run, we can show result.parameters, and we're going to see that we changed beta parameter, which was a list of the same values, and we were also changing the trap densities, which get loaded into this array. And we can also inspect this nicely because of X-array. Okay, one thing that I forgot to mention before is we can also save parametric data. So if I go back here in the last example, we can specify that we want to save parametric data or the result data sets on disk. Currently, we can also only save X-array dataset in netcdf file. But if I take a look, so we were saving this in the outputs. This is probably the last runs. Pyxel data. No. Outputs. Nope. Just a moment. It's gonna be this one because it was the first. So here we saved the dataset and logs and parameters into netcdf file on disk because we specified so in this save parametric data attribute. And in the next one, we said that we would like to save data to file. So this is the same attribute that we used yesterday for single mode. And what this does, it's going to save the array that we specified here for each of the pipeline runs. So here we said we want a fits image, and we want it for each of the runs of the pipeline. So if I go in the second one, here we have the image array in fits format for each of the runs of the pipeline. Okay, we can again do some plotting. So again, we will plot the image. We will construct a HoloViews dataset. We set dynamic to false this time, so it's loaded in memory. And here we see the image that we were actually using for the simulation. So this was just a fits file of some stars, which was and yes, if I now push this to the end, we can see the effect of the higher trap densities as smearing of the stars. Okay, and the last example in parametric mode would be sequential mode. So in sequential mode, the pipeline is run as many times as there are different parameters, basically. So at the top we had 1 to 3 and ABC, and it was run 6 times. Here I'm just going to do a very quick example of what happens if we change level, and we will plot the photon transfer curve at the end. So first, again, all the standard stuff. We pass the numpy function here, so the log space from 0 to 6, and we would like to have, I think, 100 steps. That's 92 actually. Okay, and what is different in sequential mode is that dataset result.dataset is not. Let's gonna show it. So it's not an X-array dataset straight away, but it's actually a dictionary which holds so keys are actually the parameters that we are changing, and for each key we have we save the X-array dataset separately. So if we want to see what was the result of this pipeline run, we have to type in this key level. And now we see again here level was, so it was in logarithmic scale. It goes from 1 to a million. And yeah, we can plot the PTC curve here. Very simple. So we can also do operations actually on X-array datasets. So here we're going to compute the standard deviation for images. So we have to specify we're applying this with X and Y. we want to do this for data set at level and for the image. So it's a bit, maybe a bit counterintuitive, this notation. So we're gonna try to use HV scatter now, so scatter plot, and in log scale. So we can see the PTC curve here at the end. So noise, or at least the standard deviation, as a function of level. Okay, this was the basic use of parametric mode. So there's 3 modes that you can use. Maybe I should also say that it's not necessary that we also change, we only change the pipeline arguments here, so arguments of the models. We can also input here, for example, the detector properties. So we could say here, let's change detector dot quantum efficiency, and we could also change quantum efficiency, for example. This also works. What else? So here, maybe one question would be, do we also get logs here in custom mode? We can also observe the result to .logs, but they're actually the same as the parameters in this case. So I think this is the end of this first part on parametric mode. I can welcome any questions now for this part before I move to calibration mode. You can post it in the chat.
Yes, there is a question of Fateme. Can the data be saved in ASCII text format instead of FIT?
I think so. I think it should be possible. I think we also have NumPy, binary, and FITS file. But I would have to try. So this is basically here. Can we put something else than FITS into detector imagery? I'm 100% for NumPy, and it should also work for text. But I would have to check.
We have a second question of Amit Kumar, which is, can we make a new model of parameters as it was explained yesterday?
So yes, you can add a new model here with some arguments, and then use those arguments actually here. Wait, I'm not sure if the question was if we can add a model or not.
I think it's a mix of the two. Is that you want to create first a model, and then he wants to make a variation of the parameter applied to the model.
Yeah, that is possible. So you can use the command create models of Pyxel-CM, and you can create a new model. You can specify the path. So you have to include it here in the YAML file. Then when you create a new model, you get this doc string where it says what you have to include in the YAML file. And once you include the new model in the YAML file, you can put the path to these arguments here. And then you can vary your arguments easily.
That's it. I think I don't see any more questions on the Discord or the chats. So I think you can go forward to the calibration mode tutorials.
Okay. Okay, then let's move on. I'm gonna close things I don't need. Okay, so this would be 0.5. Okay, so next mode is calibration mode. So calibration mode is used to calibrate models, as the name suggests, to optimize parameters of a certain model. And so the basic idea would be to find a set of optimal model parameters that will, when applied to the input data set, return data that is as close to the target data set. So I'm going to use the image to explain this. So we have a target data set, and I'm going to talk again about CDM model here, so charge transfer inefficiency. So let's say we have a data from an irradiated detector. So this is a flat field from a irradiated detector of the FLEX mission. So FLEX is an ESA mission for observing fluorescence on Earth. And yeah, so we got some experimental data from the laboratory. This was a flat field with overscan. And because of charge transfer inefficiency, we can see that there's an exponential curve behind this flat field due to traps in the detector. And let's say we want to know what kind of traps are here, how many species of traps are present, and what are the trap release times. So we can use the calibration model to calibrate our CDM model. So we will fit input data to match the target. We will fit target data so that when we apply our pipeline to the input data, that it matches the target. And so we got the data for different signal levels, so from 1,500 electrons to 100,000 electrons. And this can be quite heavy on computation, and so because of this, we use evolutionary algorithms implemented in the library DeMo. So DeMo is also ESA developed. We also use parallelization by using the Dusk library. So we are using multi-processing or multi-threading. And basically, in PICMO nomenclature, okay, so how calibration of the model goes in PICMO nomenclature. It basically follows the story of evolution. So each processor, so we're using multiple processors. Each processor thread is called an island. And on each island, there lives a population of individuals. So those individuals are candidates for a solution of our model. And each of those individuals at the beginning is randomly assigned with different chromosomes. These are model parameters, for example, trap species and trap release times. And the individual with the best fitness is called, so the best solution to our model, to our fitting problem, is called the champion. Group of islands, it's called an archipelago. So this is our whole cluster. And during the evolution, the population is evolved with a chosen algorithm. Each evolution consists of multiple generations, and basically it works on the principle of mutations of chromosomes. So the algorithm will mutate the chromosomes, and then the champions will get fitter and fitter. And in the end, what we get is the best champion for each of the islands, and we can find out the best model parameters. And we're going to see how it works in a minute. So we also use library Xarray to store our result data set. We're going to go through how to prepare the configuration file again for calibration mode, how to run calibration mode, and how to visualize the results. If you want to read more about PICMO or Dusk or Xarray, you can check out those links here. It will take you to documentation pages. Okay, so we can start again by importing input outputs model. We will use calibration mode function, and we're also using this display calibration inputs from Pyxel.notebook, which we already saw down here. We're also gonna set a scheduler. So this is basically the scheduler, the Dusk scheduler will process coordinate. So the Dusk scheduler coordinates the actions of several Dusk worker processes. So it will basically handle our multiprocessing, and we're using a scheduler client from Dusk Distributed. If we don't if we don't use the client, then Dusk will use another scheduler by default. But it's good to so the upside of using the client is that we get a nice dashboard with which we can track our progress, and we will see this later how it looks. And when we import the client from distributed and started it, we can already see that I have a local cluster running with 4 workers and 12 cores. I have 30 gigs of memory on my local machine. Okay, so again, we have to load the calibration configuration file. And here there's a bit more parameters that we have to specify, and I'll go over it. So the first one is the result type. This will be Pyxel. This is the array that we are most interested in, and I'm going to use it for plotting at the end. We have to specify our fit range of the input files, and also target fit range of the target files. So we have, I think, 6 files here, 6 text files that we plot the data from these files here. So we can also inspect the file names. We have to set the seed, the number of islands. I'm going to use 10 processors, so or 10 cores. So the 2 cores will be not used in this run. I'm going to do 2 evolutions with 10 generations. We are using mostly the SATE algorithm. This is just a short calibration run with population size of 20. We also have to specify our fitness function. This will be used to compare our simulated data versus target. So to basically compute how fit is a champion. In this case, it's a sum of absolute squares of the residual, so the difference between target and simulated data. And of course, we have to specify what parameters will we calibrate. So in this case, we calibrated parameters of the CDM model. We calibrated beta parameter. We have to specify the boundaries and if the parameter is logarithmic or not. And we tried the calibration run for example for 3 traps or for 5 traps, but in the end we settled for 4 traps, which gave a result good enough. So here we are fitting our CDM model for 4 different traps, and the parameters are trap release times and also densities. We are not loading an image here in the beginning, but we're gonna just inject the charge profile directly. We can do this with the model charge profile. So we are using those files here with those charge profiles to inject charge directly instead of loading the photon array. So the photon array will stay empty during the calibration. Okay, and yeah, we can run. So once we run the calibration mode, so we first construct the islands. So we will populate the islands with a random population of individuals. And then we start our evolution. And during the evolution, we can actually see in the Dask dashboard. So that's why we use the client. We can see what's going on. So first, this part was building the islands. Then this was the function evolve on 10 islands in parallel. And 12 were not in use. And we do 2 evolutions, so this is why we have 2 columns. And in the end, we save the data and compute the results. And okay, and in the end, we save the outputs. Here we can again put the same arguments, so save data to file. If we save the image array, here we're going to, okay, let's see. I'm going to go back. Tutorial, calibration outputs, this one. So here we saved the image array into fits at the end of the evolution for each island and for each of the signal levels. So this is noted here with the processor from 0 to 5, so 6 different files for each island. And again, island is the processor, core or thread. We also save the dataset, which is the output. This result is again a named tuple, and we can again access the dataset like this, similar to parametric mode. And we also save the logs in CSV and Excel format, but we're going to look at this later. So what we actually save, we can inspect here. We have the target data for each of the signal levels. So the ID processor and as a function of Y and X. We have the simulated data, so simulated arrays, image, signal, and pixel. And we also have information about champions for each evolution and island. So their fitness, the decision vectors. So this is the change from the last evolution or the last generation, last evolution, and also champion parameters. And we will use this data set to plot our outputs. We can also inspect logs. So what we don't save here in the data set is champion fitness for each generation. So if we want to retrieve that, we can go into logs. So here we see number of generations, number of evaluations, best fitness at the island, and those are the parameters of the state algorithm that were changing during the evolutions. And yeah, if we specify here that we want to save this data set to disk, we can do it like so. So save calibration data. We can also save logs into different formats. Okay, and how does it look once we actually open up the data set? So here I'm going to import some more functions from Pyxel.notebooks. This will be display simulated, display evolution, champion heat map, and optimal parameters. We're gonna use again HoloViews and bokeh once we import those. And we can use the the X-array function open dataset to open the netcdf file. And I'm not going to use the file that we just computed here in the previous notebook, but I'm going to use a file called long calibration. So this was a longer calibration that we did to calibrate this flex data. We also save here, besides the data information about the champions, we also save information about other good individuals, or the best individuals. In this case, there were, beside the champion, we also saved 20 best individuals for each of the evolutions, just because the plots look nicer then. So you can add this here with this argument, non-best decisions. We ran this on a cluster of computers on ESA grid with 160 threads, population size 250, and we did 125 evolutions. So this is the attributes. This is the metadata that you can add, or gets added automatically in calibration mode. We used a fully connected topology between islands. So topology is when islands are communicating between each other during the evolutions. So they communicate the information about the best champions from their population. And we also save the result type. And yeah, this was done for 9 different parameters, this calibration run, and it was running for 16 hours, I think, overnight. Okay, so we can compare target and simulated data with this function display simulated. We pass in the output data set that we loaded before. So this is now the simulated data. So this is computed using the parameters from the best champion. This was the target data that we wanted to recreate. We can also plot the overlay. And yeah, I can change here to different signal levels. And we can see that this is not just a single exponent as we predicted. There's multiple slopes to this exponent, so we know that there's more than one trap, or more than one species of traps. And this, in the end, if we change the island, it shouldn't change because we have the fully connected topology, so the islands are communicating. We can also plot the residuals, so target minus simulated, to see if there are any preferred signal levels, or if we have any spikes. For example, here, yeah, we see a bit of a spike. So actually the calibration mode preferred the lower signal levels a bit more, but I should normalize this probably. This is just to make sure, that we are not putting too much weight on one of the signal levels. We can also use the function display evolution to display fitness as a function of evolution number. So this, for different islands, it was changing a bit differently. So we see in the beginning the fitness drops very quickly, and then it's basically nitpicking since from evolution number 60 and on. We're just trying to find a bit better solution. And we can also inspect the parameters. So here we see that this is fluctuating in the beginning quite a lot, and then it evens out towards the end. And this parameter IT goes from 0, so this would be beta parameter at 0. It would be 1 to 5 for the trap release times. and 6 to 9, it's 6 to 9, yeah, 6 to 8. Oh no, 6 to 8. 5 to 8 for the densities. Okay, then this is an interesting plot. So this is the heat map of champions. Oh, that's it, I think. Here we plot the values of trap release times. So this is X versus fitness, and the color denotes the occurrence. So how many times does a certain solution come up? So in the beginning, all the parameter space is quite evenly populated. So we have this random population, and once we run the evolution, the fitness gets better and better. And then in the end, we can actually see that we get 4 separate solutions for trap release times, and they get concentrated in these 4 dots at the end. So this is in the end our best solutions from this calibration. So here we specify that we use the champion heat map function. We pass the data set. This is a number of bins for the histogram. This is basically a histogram, a 2-dimensional histogram, and we use the logarithmic x-axis. And the parameter range was from 1 to 5, so we only plot here the trap release times. And in the end, we can use the function optimal parameters. We pass the data set, and we can see from which island and from which evolution do we get the best champion. And here is the solution, so the final parameters that we can use then to in other pipelines. So for example, parametric mode. So this would be beta parameter, the 4 trap release times in seconds, and the 4 densities. Okay, and I think this is it. So here we didn't have a 2-dimensional array. It was only, we only did calibration in 1 dimension, but we can also do calibration in 2 dimensions. I think there's one example in calibration in Pyxel data example slash calibration. It's also a 2-dimensional case. And I think with this, it's time for questions.
Thank you, Matej. Do we have any question? I don't see. Okay. We have one of the chats, had Hamed. Which fitting parameters should you prioritize if you want either speed or accuracy in terms of number of evolution of population size?
So which parameter should we prioritize? Well, so speed depends on the model that you use. So first you have to make sure that the model is quite fast, because pipelines are run a lot of times during the calibration process. And then I think you just have to try with how many free parameters do you have. I think less parameters, easier it is to fit. So the faster we will get a solution that is valid. Here I think it was quite a lot for 9 parameters. It was quite hard actually to be convinced that this is a good solution. So we had to play around a bit for a while. And of course, you can do shorter runs. You don't need to do a full scale 16 hours calibration straight away. I mean, it's quite fast. You can do maybe a few minutes to start and then go from there.
Okay, and so another question from the same author. Related to this, how do you know how good your solution is? Can you get uncertainties on the fitted parameters?
So for the uncertainty, I'm not sure actually. So one good way is to basically the question is how are you sure that these are not the global? How are you sure that those are global minima and not local? And we are not just getting stuck in the local minima, and maybe there is a better solution. Yeah, I don't know, to be honest. There must be.
Yes, maybe I can try to answer that.
Yes.
We're really using the Pagmo library, and they provide different kind of algorithm to converge. So we're using one, SAD. Of course, yeah, we should try different. I think it would be also possible eventually to use several algorithms at the same time to see which one converge faster or better. So yeah, this is still to be discussed, but we're really using a Pygmo, which seems to be a really good library.
Thank you, Frédéric.
And in the output, you have all what you need to compute the uncertainties. I mean, with the fitness map and for each evolution, you will also have the results for all your. You can extract
all the islands.
functions. Yeah. So you can compute the uncertainties. I mean, we have the residuals. You are one step away from the chi-square, for instance. So it's not a built-in function, but you have to do it in your analysis, basically.
Okay, do I see any more questions?
I think it also depends a bit on the topology you use, right?
Okay, I don't see anything else. So thank you, Matej.
Okay.
Maybe I will go to the dynamic mode.
Yes. Take
Okay.
it away. I will stop presenting.
Okay. Check. This is the correct one. Jupyter Lab. Do you see my web browser with Jupyter Lab running?
Yes.
Thank you. Okay, so let's start on the dynamic mode. This is the last tutorial that we have. So just a little bit of history on the dynamic mode. Initially, Pyxel came with a single mode, the calibration and the parametric mode. And when I first heard about Pyxel, I bothered David Luxani, which was one of the developers that was with us at the time, to have something for the that could be applicable for the Hawaii detector, which are working with non-destructive reads, which means that I was not satisfied with a single mode, not satisfied with the calibration or the parametric. What I wanted to do is to take my detector object, like I see here, and I wanted to feed it to the pipeline and then refeed it to the pipeline and refeed it to the pipeline with different time increments in order to build the non-destructive reads of the Hawaii detector. So a few days later, we had the dynamic mode, the first iteration of the dynamic mode, which asks you for the number of iterations that you want of the detector object through the pipeline, the time in between two steps, and if you are doing non-destructive reads. So if you are resetting your detector in between two reads or not. I tried to standardize the Jupyter notebook as Matej is doing, meaning I'm trying to have X-arrays as an output of the dynamic mode to have the same kind of display for everything, but I'm not as skilled, so please bear with me. Okay, and so what I want to do on the dynamic mode, so I have a specific display for the dynamic mode. I load everything. I load all of views in order to have the display. I have my dynamic mode YAML file. So if I take a look at this YAML file, what's important is the configuration, which says I have non-destructive readouts. I'm doing 10 iterations with 0.5 second between iterations. I'm loading everything. I have my dynamic mode, my detector object, and my pipeline. I'm running the dynamic mode, which is here. You have a nice progress bar over the number of iterations of the dynamic mode. And then at the end, I have my dataset, which is an X-array, as you can see here, with the dimension X, Y, and T, which is a time, which is, so it's a 0.5 second increments, and you have 10 iterations, so it stops at 5. The pixel, signal, and image array. And then what's interesting is that you can plot everything using the all views. So you can load your X array, try to create an all view dataset from this. And then you can try to display it like this. So what did I do is that I took a detector. So I take the YAML file. I took a detector. I was loading an image of the Pleiades, which is very big. So I did have to, there is some automatic cropping here because I only have a detector of 450 by 450. And then I'm doing all of the simplest models that we have in order to complete the pipeline. And this is what you can see here. You have my detector, well, my first iteration of the pipeline. And here you have a little slider which shows you the integration of signal, where you have more and more signal until the 10 steps of the iteration. Yes, okay. And so what you can do with all of you, which is very nice, that you can define regions of interest. For example, here I defined 3 little regions, 1, 2, and 3. And I will be more interested into the second region here, which is 5 by 5 pixels. I select this region and I plot it, so you can see the integration of signal. And what I really like to see with the WISE detector is to see the integration of signal. So I want to, on this region of interest, I want to plot the integration of signal of the detector. So you can see here on this 5 by 5 grid, you can see the integration of signal over the 10 steps of the dynamic mode. So this is the basic tutorial on the dynamic mode. But I thought what would be best would be to show it to you with an actual model running on it. So for that, we are going to go to not the tutorials, but the examples. In the dynamic mode, there is a dynamic persistent H4RG Jupyter notebook that you can open. So in this notebook, I'm using the dynamic mode in order to simulate persistence. So what do I need to do in order to implement persistence inside of Pyxel? So the first thing that I need to do is to create some kind of memory inside of the detector. So what I did is that I created an attribute on the detector object in Pyxel, which is the memory attribute, which you can use to store temporary results of your detector. And for me, I'm storing the amount of charge that are being trapped by persistence by my detector. So if some of you are not familiar with the persistence effects, when you do the integration with a WISE detector, sometimes you would observe a bright source, so a star right in the middle of your field. You would reset your detector and do some dark, and you would see some persistent signal at the place where your bright star used to be, which is a big problem because depending on how of the amplitude of persistence, it can dominate another source that would be exactly at the same position. And this persistence is a memory effect, meaning you have charges that are being trapped inside of the detector, and they are being released once you reset your detector. So if you want to replicate to observe persistence, you would do a reference dark, observe a bright source, and then you would see on the reset of the detector and your other dark, you would see the dark plus the signal of persistence. And this is what I want to show you how it can be done with Pyxel. So inside of my detector object, I created my memory where I do have the trapped charge that is being filled while I integrate the detector, and that is being used for detrapping process in order to create persistent signal. So I'm not going into details of this model voluntarily because tomorrow there will be a talk by Mark Nisser and I don't want to spoil everything for you. So for the persistence data, I do need some data from the characterization of the detector. So I had some data provided by Liz for the characterization of the Moon Z4G engineering grade detector. So this is the kind of map that you would have once you do the dark subtraction and you observe just the persistence created by a flat field illumination. So you would see that persistence, well, at least on this detector, displays a lot of different features. And you would have what is interesting for this simulation is that I'm working on a subset by 450 or by 450. So what I would need to do is to load this part of the image. So you can see you have some border here that you can identify some cosmetics on the detector that we will see later on persistence. How I do it? So I want to replicate exactly this observation scheme. So I first want to do an exposure where I illuminate my detector, then a second exposure where I cut everything and do a dark with 0 photons per second and see the persistence. So for that, you can create two different YAML files. The first file will have a source, which is my image of the Pleiades. And the second, what you call dynamic dark, as a source, it does have dark underscore data.fits, which is only zeros, very simple image. So I go back to my Jupyter notebook. Okay, so first I want to run the dynamic mode. So I load the dynamic mode with a source. So I expose my detector to a bright source. I run the dynamic mode. So I have 20 iteration here. It's a very low time step. So I will only be filling traps with short time constant. And then I want to, okay, so I display my final data set, which is my X-array. And so what I did is that here you can see my detector object. You can access the memory, and I want to access the persistence part of the memory. And I have a small function here which displays persistence, and it's displaying the amount of charges trapped for each time constant that I defined. So in this model, I defined time constant of 1, 10, 100, 1,000, and 10,000 seconds. So I did an integration of 20 steps with a 0.5 seconds integration, meaning that on persistence, I will most likely have more charges trapped on the lowest time constant than on the highest time constant. And what you can see here is that the first, so the 1 second time constant, you have 25 charges in median. 10 second, you have around 10 charges. But then if you go to 100, 1,000, and 10,000, you still see the structure of the persistent map that I've loaded, but you can see that the amplitude are way less. So I have almost nothing trapped because I didn't expose the detector enough. So I would still have signal from persistence from those traps, but not as much. So then I want to display the data with all of you. So it's exactly the same as before, but I have more steps. So I'm close to saturation here. I'm displaying the pixel by pixel illumination. So this is what I said at the beginning. I'm exposing to the detector to a bright source, so you can see the integration. And now the fun part, which is the persistence decay. So now I have my detector object here, which I expose to a bright source and which trapped charges. And so one very neat thing that you can do, at least on the Jupyter notebook, is that you can then load the dark, the dynamic dark YAML file, which has a different source, which is only zeros, but you don't load the detector, which is why I specifically commented it out. This time I don't load my detector, meaning I don't initialize a new detector object. What will happen is that when I run the dynamic mode, here, I'm using the previous detector, which already trapped charges. And so this is exactly what I want to do, is that I integrated my signal with a bright source, I reset my detector, and now I want to see what will happen to the trapped charge if I expose my detector to nothing. So this one, so if I take a look at dynamic dark, here I had 40 steps, 0.5 seconds. Well, almost the same, but a bit more time for the decay. And so I run my dynamic mode, and I take a look at the memory of my detector. And what's interesting is that you see I've roughly have 20 seconds of decay time, of integration time, and during those 20 seconds, I almost completely decayed the 1 second time constant, almost the 10-second time constant. So it was at 10, now it's around 1. But the 100, 1,000, and 10,000 seconds, they decayed a bit, but you don't see it because I only have 40 seconds for the exposure. And so now I'm using the displays that I was using before, which is first trying to take a look at the image of the detector. So you can see here, instead of having just the image of the playheads on the detector, you can see also the persistence map here feature that are displayed on the detector. And as I increase the signal, the time, so first iteration, second iteration, third, and then it doesn't increase anymore. So what did happen exactly? So for that, I'm taking a look at my region of interest, which is a 5 by 5 pixels. And you can see here exactly what happens. You have a bit of signal that's being decayed in the first iteration, and then after a while, I don't have anything more to decay. So you see exactly the persistent signals that I illustrated. So if you take a look at this, and this is exactly what I try to see here. So I will not say that I have a complete working persistence model. I do know that I still have some errors. One of them that is pretty obvious is that apparently I have a problem with saturated region. And I think it's coming from the fact that I saturate the detector. And in my persistence model, at one point, I subtract the amount of charge trapped to the pixel array, and I think it's just subtract everything, and so I have some kind of, I'll say it, divergence of the model. And depending on which iteration I have, either I have very low persistence on those pixels, or I have maximum persistence. So this is one of the errors that I had identified. I'm still working on this model, but at least it looks like it works. Do I have something else? I don't think so. I think that's last thing on the persistence. Yes, and on the dynamic mode as well. So I will take question now if you do have some. Nothing?
Can I ask a tricky question?
Sure.
How do you plan to calibrate your persistence model using the dynamic mode?
So that's one of the questions, one of the discussions that we started with Matei, is that the calibration mode and the dynamic mode are separate for now. But what we want to do in the, well, let's say medium term, is to be able to use the calibration mode to find the parameter of the persistence model using data sets of persistence, yes.
There is a question in the chat also.
How do you extract the time constant from your data? So currently, we provide the time constant, meaning we fix the time constant to 1, 10, 100, 1,000, and 10,000. And start using that, we fit a model to it. So we have the amplitude, the number of traps for each time constant, which is different.
There's actually, sorry to interrupt. So there's actually a couple papers on this, which are available on the archive. But essentially what you're doing is you are creating bins of time constants. So you're saying, you know, how many traps have time constants in the 1 second bin? How many traps have time constants in the 10-second bin? And essentially what you're doing is you're treating every trap as an individual that falls in one of those bins somewhere.
So if you want more details, if I remember well, I did put on the model a link to the paper from Simon Tulloch that was the one that came up with this first iteration of the model. But if you want more detail about the model, I think Liz is the perfect person to talk to because she was the one who did the analysis.
Yeah, and actually Mark will go into some detail tomorrow about how this then gets used for actually correcting science data.
Okay, I think we don't have any more questions. Of course, if you have more questions about the dynamic mode, even on persistence or calibration mode or parametric mode, please go on the Discord. We are all there, and we will be happy to answer your question or to guide you if you are trying again the tutorial and encounter some errors.
Okay, so that was the last tutorial section. So I want to thank everybody for attending. It's been really great to see so many people interested in using Pyxel. And as Benoit said, you can always join us on the Discord to ask any pending questions you might have. And also, you know, feel free to try out some of these tutorials and examples on your own, and you can always ask us later as well. So with that, I'm going to end the recording, and we will see you all tomorrow for session number 3 of the detector modeling workshop.